So for the homework this time, as previously mentioned, you sent an email saying you did the homework. The additional homework starting now will be using WebAssign, which I set up. So I imported some Excel file that had everybody who's registered for this class. It had their names and email addresses in it. And then according to WebAssign, it added you as members of the WebAssign version of the course and sent you all emails. So if you check your official UW email, you should have received a message, I guess. And you're shaking your head?
Yeah.
Okay. So according to it, it sent 50 emails. I made a first homework assignment where I chose, I don't know, it seems like every single question was basically just compute something and put some numbers in a matrix. So I made up a couple of questions that involved a little more thought that weren't purely calculational, because the ones that they had pre-made were all just like multiply this matrix by that matrix and stuff like that. The ones that I made up are multiple choice, but they're so obviously if you want to just get the right answer, you can just, since I set the number of guesses you can make higher than the number of choices, you'll have no trouble getting the correct answer. So it's much more about trying to figure out what the right answer is and then being sure that you understand why it's that. I mean, so for example, one of the questions is, can you ever have, well actually I can't state it yet because it involves words from today, but well, here's one. Is A plus B transpose the same as A transpose plus B transpose? So this is just one of the questions I gave. There are two possible answers, either yes or no. You can guess 10 times. So you'll have no trouble getting credit for this question. What you want to do is make sure that you really believe and understand the answer that you give, and maybe write your own proof up or something explaining why. Yes?
I never used WebAssign before. Do I have to do it only one time and in a limit time or anything like that? How many times can I submit my answer and do
Each answer can be submitted up to 10 times, I think.
Do we have the limit time that I have to complete it in that amount of time?
I don't, there are, I know there were some listed times there. I don't know if those are enforced or what, or if they're just like averages, or I couldn't tell. What? Okay, he says it's usually not timed. It did for each of the questions it had a time next to it when I was selecting them, and I think that might be possibly, I don't know what it is actually, but yes?
I believe that's the supposed time it's supposed to take you to do the question.
Yeah, I mean it could be because they have the data. When anyone uses the system, I don't know if they actually do anything that clever. I kind of doubt it based on what I've seen, but they could actually just see how long it takes people to answer the questions and then compute the average and tell you. Based on that, it looked like it would take about an hour to do the homework assignment. So, for what it's worth.
Is this the one due next week?
Yes, I'm talking about only the one that's due next Wednesday at 11:59 p.m. Yes?
On the course website, the file with the lecture notes
Yes.
are all written in code.
Yep.
Is that like intentional, or is it supposed to be like this?
That's so this worksheet, for example, right here, uses a program that I had not released yet, which I wrote to display them. I actually made it available a few hours ago. Probably full of bugs because it's not ready for release, but if you want to try it out, you can go here. It's cloud.sagemath.org. With the caveat that you can go here, you can make an account and start using it. I very much reserve the right to reset the machine that this is running on at any time. So if you upload something there, don't expect that your data will not be deleted at some point right now. This is very much a preliminary thing. But anyways, if you go here and make an account, you can then make a project and then click upload and upload files that I've created, like this one today. Okay, so yes?
For like a problem like this, like the A plus B transpose equals A transpose plus B transpose, I feel like on like the homework, what I'd probably just do is like some simple like example matrix and then, you know, just solve it and see if they're equal. But should we try to like go about it like trying to like prove it or?
I think that would be a good idea for this one. Yeah. Yeah, that's what I recommend. And as you can see here, and in a moment on the next slide, I will show you how to carefully prove a very similar statement with multiplication instead of addition. And it's exactly the same process for a lot of these problems. Okay? It's really kind of a calculation where you don't know the number of rows and columns of the matrix first. So that's kind of an unknown as well, or a variable as well. So if you pay attention today, you'll see a technique for addressing this sort of question carefully. All right, so we're going to talk about two things today. Just about homework. We're going to talk about symmetric matrices. We just barely touched on them at the end last time, but we'll finish talking about them today. And then we'll talk about inverses of matrices, which I haven't done anything with them yet, except somebody in the audience mentioned their existence, like on day one. Okay, so that's our plan for today. We'll see how far we get. I think we should get everything done though. So first, transposes. So we'll talk about both symmetric matrices and the transpose of a matrix. Oops. So if you have a matrix A, I've already defined a transpose. And this is the matrix you get by reflecting along the diagonal. So if the matrix A has entries A, I, J, then the matrix A transpose has entries A, J, I. So for example, the 2, 5 entry of the transpose will be the 5, 2 entry of the original matrix. If you view your matrix as kind of having a coordinate system, so that this is position 1, 1, then 1, 2, and so on. 1, 3, 4, and 5. So I guess this is like the, kind of funny. So, kind of annoying actually, because if it were x and y coordinates, they're backwards. So that is 3, 1, 3, 2, etc. 3, 5. It's kind of like a matrix is like an Excel spreadsheet where each of the entries is a number. And in an Excel spreadsheet, you have numbers that refer to the rows, and then the columns, they use letters instead of numbers. But in a matrix, you just use numbers as well. Okay, so this is like, actually I messed up. Very used to counting from 0. So see something that's fourth one, I put a 3. Okay, so this is like row 1 of the spreadsheet, row 2, row 3, and row 4. And then this is like column A, column B, column C, except in math, or except with matrices, you use column 1, column 2, and so on. And the transpose is what you get when you just reverse. You just take the new matrix you get by reversing all of the coordinates. Okay? So we already did this. The transpose of this one is, I just want to make sure you remember, 1, 3, 2, 4. Just get it by reflecting that way. Reflecting across that diagonal. That's the transpose. Now there's some properties of the transpose. It's an interesting thing to use for various reasons. One reason being that if you have a matrix that's symmetric, namely A is equal to A transpose, then all kinds of things will be true about that matrix, which will not be true of a general matrix. It'll make various things much easier. I can't go into it yet, but when we start talking about, for example, eigenvalues, then the properties will be a lot different than a general matrix. Yes?
When you go and try to transpose a matrix that's that dimensions,
Yes.
you have 1, 5,
That's right.
corresponding 5, 1 doesn't happen. Does that value get destroyed?
Nope.
Or does it turn into a different?
It turns into a different shape matrix. Great question. So if you have a matrix with n rows and m columns, so if A is an n by m matrix, then a transpose is an blank by blank matrix. What do you want to put in that blank? M by n, but that's correct. Sorry, I'm not answering your question. Yes.
N would have to be equal to M for it to be symmetrical.
Yes, that's right. There's no possible way a matrix could be symmetric without n equaling m. So this implies that n equals m. And one way to make a symmetric matrix from any random matrix at all is to take a matrix and multiply it by its transpose. So, and this always makes sense to do. So let's see, I'm gonna have room. Oops. Right here. Fact A times A transpose is symmetric. We should also check that this makes sense. A, let's say it's an n by m matrix. Then A transpose is an m by n matrix. And it makes sense to multiply two matrices if when you write their dimensions next to each other, the numbers that are right next to each other are the same. And m is the same again. So it does make sense to multiply A by A transpose. A does not have to start out as a square matrix for this to make sense. For example, if A were a matrix with one column, its transpose would have one row, and you can multiply those two together and you get a 1 by 1 matrix. Yes?
So is it always true that the ones on the outermost side, the n and n, and n and n are the reduced matrix?
Yes.
When you multiply?
Yep. These two have to be the same, and they completely disappear from the picture when you multiply them. So, yeah, the dimension of the resulting matrix will be, so if you take a n by m and multiply it by an m by r, the m's better be the same or it doesn't make sense, and the resulting matrix will be n by r. Okay. So here the product will be n by n, and it's symmetric. And let's, I'll tell you why this is true. It's true because it follows easily from a more general fact, which we'll prove, namely that if you have any two matrices A and B for which this product makes sense, then AB transpose, you multiply the two matrices together and then transpose them, it's exactly the same as B transpose times A transpose. So you kind of would want something like this to be true because it kind of looks like what happens when you raise something to a power maybe. Note though that the order switches. It's just, this is what is true. If you put the order in the other way, it doesn't even make sense to multiply the matrices in general, but it's also not true. So there it is. So this is true, and we'll just prove it by writing out the formula for matrix multiplication and the transpose. And we'll do it on both sides and check that things work. But before using this, let's apply it to see that A times A transpose is symmetric. Okay? So I'm going to check that this has to be true. So we'll leave this for a little bit, and we'll come back to this. So we will return to this. So I'll try later. By later, I mean in about 3 minutes. So not much later. So A times A transpose is symmetric. I'm going to convince you of this fact beyond any possible shadow of a doubt, assuming you believe the thing I circled. Okay? That's my goal. Shouldn't be hard. All I'm going to do is try to, basically, what does it mean to be symmetric? It means the matrix that you're considering, that you're making a claim about, is equal to its transpose. So here's the thing we're interested in. Here's its transpose. There's really only one thing I can possibly do at this point. Since I've circled this statement over here, I haven't proved this to you at all, but I'm going to try to apply this to something over here. Should I try to apply it to this or this? Which of these two things, the one on the left or the right, looks more like what I've written over there and circled? On the right, yes. The thing on the left is not a product in the whole quantity transpose, but the thing on the right is. So now let's simply apply it. We're going to make, this is kind of like a formula for any A and any B, you have this statement. So I'll make A equal to the A I have over here. What am I going to set B equal to apply this? What? B to A transpose, that's right. I'll make the B right here A transpose. Okay, and then what that tells me is that this is equal to A transpose times A transpose transpose. Did I do that correctly? What? Okay. Did I do that correctly? I messed up every possible thing there. So let's be more careful. A transpose transpose times A transpose. Okay. Do you believe that, at least? Yeah. All right. So first, what do you think happens if you transpose a matrix and then transpose it again? You just get back to the original one. So you get A. And you write this as A times A transpose. Oh, whoa. That's exactly what I have over here. Boom. A times A transpose is symmetric. It's kind of surprising because if you just take a matrix, multiply it, lots of entries, and multiply by its transpose, you just feel like you're messing with some big mess. But at the end of the day, the result will be a symmetric matrix. You take any matrix at all, multiply by its transpose, and you get a symmetric matrix. So that's what we just checked. Except we haven't verified the circle statement. But you can see how this could be useful. Just an example of how it's useful. So now we need to check that, in fact, A times B transpose is B transpose times A transpose. Right? No, don't you want to know why that's true now? Because that's not really, how can you check? You could certainly try a few examples. You can do some special cases, like if A and B are 1-by-1 matrices, then this is really easy, because 1-by-1 matrix is just equal to its transpose. So that does absolutely nothing. And multiplication of 1-by-1 matrices commutes. So that's easy. But what if they're 2-by-2 matrices? Well, then you could make a generic 2-by-2 matrix, A, B, C, D, and another one, E, F, G, H, and multiply them together and then transpose. But you get a big mess. It would work out, but it's kind of tedious to try to convince yourself that this is true for all possible matrices A and B for which it makes sense by such arguments. However, if we simply write down the definition of the ij entry of the product of two matrices, which remember I introduced to you before, earlier this week, then you just do it on this side, and you do it on that side, and you just notice a little algebraic identity, then it will give us that this has to be true for all matrices. So let's do that. And I've written it on this slide also, right here. Okay. So let's prove beyond any shadow of doubt that what I circled is true. I'll just recopy it somewhere. So claim or call it proposition. Something that's either true or false. A, this one's true. A times B, a statement's true or false, and a proposition is supposed to be true. A, B transpose is B transpose times A transpose. And then here's why. And basically, part of this is that you should understand why this is true for any matrices A and B for which it makes sense. And when I say understand it, I mean you should be absolutely convinced. This isn't like a calculus class where you're sort of convinced, but at some point there was an epsilon and a delta, and there are all these real numbers, and you don't actually know what any of it is, which is the case when you take calculus, because you don't rigorously develop the foundations. But in linear algebra, I mean, none of that's there. You can literally just understand why everything is true if you put in some effort. So it's, in a sense, it's more abstract and harder than calculus, but on the other hand, you have the chance to understand absolutely everything in this course. Whereas in calculus, it's just not possible unless you do a whole bunch of extra work. There's another class you might take later called analysis, in which you carefully understand why the things in calculus are actually true. Okay, so here's why this is true. So if you have a matrix A and its entries are Aij, then the entries of the transpose are Aji. So that's, in other words, like the Ij entry of the transpose is little a sub Ji. I hope that you don't find that too confusing, but let's figure out what is going on here. So the other thing is that if you have a matrix A and a matrix B, the other thing I'll use, we've written the ij entry of A as aij, and the, I'll say the jk entry of B as B sub jk, then when you multiply together these two matrices, the ik entry of the result, A times B, the ik entry is simply the sum aij ejk. So, and it's the sum as j goes from 1 to whatever makes sense, which would be the number of columns on that. Okay? So all this is again, for the fourth time, it's writing down a formula for taking a row and a column and multiplying the corresponding entries together and then adding them all up. That's what I've just written down there. Okay, so now let's try this out. So what is the, we're going to take, let's take I and k. We're going to try to figure out what the ik entry of both sides of this equation is. And if they are the same, then we'll prove that this equation is in fact an equation. Okay, so we're really interested in two quantities, A, B transpose, and B transpose times A transpose. Those are our two objects of interest, and we want to know what the heck is the ik entry of this, and what's the ik entry of that. If the ik entries, if we write down a formula for the ik entries of each of them, and the two formulas are obviously equal, then we'll know that the ik for any I and k entries of these two matrices are the same, and hence the matrices are the same. So let's see what we can do. So we want to know the I comma k entry of AB transpose. That's the same as the k comma I entry of the product of the two matrices before you take the transpose, right? Because that's what happens when you transpose a matrix. The ij entry of the transpose is the ji entry. You just switch the order of the indices. Okay? I hope that you're not. I didn't pull a fast one here. Okay. There's a formula for the whatever comma whatever entry of the product of two matrices. I just wrote it down, so let's write it down. It's the sum. You have some variable, it's called j, going from 1 to m. And now you have to be careful. It's just like before when we had an a and a b and we made b equal to a transpose. You just have to be careful what's being substituted in. So here, it's a, that's the first matrix, and then k comma j times the second matrix, these entries, b sub j comma I. And again, remember that's because I want the k comma I entry, so think of it as the first and then the second entry. And here, the first entry I just happen to have called I up here, but what happens is the row, that's the first subscript of the first matrix's general entry, and the column is the second subscript of the second matrix's general entry. So there it is, that right there, all the work I really had to do for this side. This is just writing out kind of what happened, the general ik entry of the transpose of the product. That's what it is, that's a formula for it. All right, now let's just do exactly the same sort of thing, but over there. And if we're careful, then we should end up with the same, with equivalent expressions. They won't be exactly the same, but they'll be easily seen to be similar. They won't be identical, but they'll be equal. So for this one, again, we have to write the I comma k entry of the product of two matrices. We have a formula for the product of two matrices, and all you have to do is just be very careful in applying this formula to that, to this product over here. Okay, and if we do that, it will work. If we don't, it will. Any possible mistake we make will hopefully mean that this won't work. So, this is going to be the sum, or some variable which we'll call j, going from 1 through m. And now we have to write down the I, comma, j entry. So we're trying to, we're trying to compute the ik entry of this product. So you have to write down the I, comma, j entry of the left matrix. So I'll just write it very slowly and carefully, one step at a time. The I, j entry of B transpose. We'll write down a formula for that in a minute, but let's do this really, really carefully, one step at a time. And then the other matrix, A transpose, will take the J sub K entry. Does that work? Yes?
Why do you make it uppercase in that case?
So I'm using some notation. So if I write, for a matrix B, if I write B sub ij, I mean the ij entry of the matrix B, which for this particular matrix is equal to, I just happen to have called it little b sub ij as a number. And I'll put parentheses around it to emphasize that, I mean the ij entry of the matrix. I just want to avoid any confusion because we're going to then figure out what the ij entry of B transpose is in terms of other things that we have. So maybe if I write the next step, then it will help. Okay? So this expression that I have here is equal to, let me just write one more step and that will hopefully answer your question. What is the ij entry of B transpose? Assuming that the entries of B are little b sub ij.
Ji.
That's right, b sub ji. What is the j comma k entry of A transpose? Right, A sub kj. Does this sum look anything like that sum to you? It worked. The only difference is that this product is in the other order. But that doesn't matter because these are just numbers for which you have that the order of the product doesn't matter. So these are equal. So for any I and k, the ik entry of this matrix, AB transpose, is the same as the ik entry of this matrix, B transpose A transpose. Which tells you that those two matrices are the same. And this is a completely rigorous proof of the assertion that A, B transpose equals B transpose A transpose. So we just proved this. This is a rigorous proof. So basically a proof is a rigorous proof, just to emphasize this, is a precise argument that would convince anyone who spends the effort to actually read it carefully. Anyone, but absolutely anyone has to be correct. But there's also a lot of use for just an explanation for why something is true. And primarily, if you don't have, honestly, if you haven't taken a course in which you learn how formal mathematical reasoning works and logic, like implications, and there's all kinds of stuff in logic, which you really kind of have to practice really hard. It's not possible to really, really carefully read proofs and understand them. But you can certainly understand the idea of an argument that convinces you beyond a shadow of a doubt. And that's what this is. So there's just no way that you're suddenly going to produce some matrices A and B for which this doesn't work. Because all you have to do is just simplifies and they both come out to be the same. Okay, any questions about that? So make sure that no matter what, you do an argument like this, but with plus instead of times. It'll be easier, but make it just as rigorous. Okay? Will everyone do that? Good. Take out a piece of paper when you get home and just write down something with all these subscripts, make sure it all works out perfectly for addition instead of multiplication. And thus concludes talking about transposes and symmetric matrices. Okay, and now on to inverses, which we won't have the time to finish probably, but we'll get pretty far along. Inverses. All right, I'll start it. Okay, so if you'll remember back to day 1, we had a system of linear equations, and we rewrote it as a single matrix equation, ax equal to b. And then we compared that to what you would do in algebra, where you have an equation like little ax equals b. And in algebra, by which I mean high school algebra, you would solve this by maybe multiplying both sides by 1 over a. Doesn't matter in which order you do it in algebra class, because numbers commute. And you would end up with x equals b divided by a. And you'd be like, wow, I can just solve the equation this way. So it might have been you might have had a constant that you had to subtract from both sides to get it in this form, but this is how you solve a linear equation in algebra. And you can do something similar in linear algebra, which turns out linear algebra is more than just doing algebra with linear equations, with one of them. So you can multiply both sides of this by, say, the inverse, whatever that means, if it exists. And we'll define it in a moment. And then what happens is you end up with x equals a inverse b. And then that solves your equation. So this is a funny thing, though. So I will define in just a moment a notion of the inverse of a matrix, and we'll prove that it's unique, and we'll see how to compute it. But you'll see that the algorithm for finding the inverse of a matrix is much, much harder than the algorithm we already have for solving this system. So you don't want to just solve a system of equations by computing this inverse and then multiplying. That would be a very, very hard way of solving a system of equations. It's somehow n times too hard. However, there are a couple of major surprises in that, well, the first one that's not too surprising is, what if you want to solve a system ax equal to b a whole bunch of times for lots and lots of different values of b? So maybe you have a 4x4 matrix A. So it's not too big, maybe with 4 rows, 4 columns. And then you have 1,000 different vectors b for which you want to solve the system. If you could find some notion of inverse, you can do all of those solves by just doing a single matrix multiply for each one. In fact, you could even make a matrix whose columns are all the 1,000 different vectors b for which you want to solve the system, and all you do is you multiply the inverse of A times that one really wide matrix, and the columns of the resulting matrix would be the solutions. And that would be a lot better than computing reduced row echelon form 1,000 times separately. So that's motivation for wanting to have some understanding what sort of matrix you can put here so that when you multiply, it cancels things out. It could give you, and it does in fact give, a much, much better way of solving ax equal to b if you need to solve it for lots of different b's, which could very well be the case. Second, it turns out that the fastest algorithm there is for solving ax equal to b, which is certainly not reducing to reduced row echelon form, involves solving this equation modulo a prime number, which I don't know if that means anything to you or not, but if it does, what you do is you do all of your addition and multiplication, and at each point you always divide by a fixed number and take the remainder. So it would be kind of like on the clock up there, when you do arithmetic, like if it's 9 o'clock and you add 5 to it, what time is it? It's 2 a.m. or 2 o'clock. But notice what happened is you do the arithmetic, you do 5 plus 9 and you get 14, and then you divide by 12 and take the remainder, which is 2. So this is what it means to work modulo 12. So you do something very similar with a matrix like with this problem. If you have, say, a very large A and a large B, what you do is you solve it by kind of maybe not working mod 12, but you work mod some other number. And it's really easy to do that. And you do it repeatedly with lots and lots of different values of B, but with the same A, maybe hundreds of times. And it's a sort of iterative process. At each point, you find out what value you should plug in the next time, and then you put together all those results, and it gives you the possibly enormous and terrifying looking answer X. So it turns out that is the fastest in practice way of solving these systems. It's implemented in a library called IML, the Integer Matrix Library. If you want to look it up, some master's student at Waterloo wrote it, but it's blazingly fast. It's like well less than a second for a random matrix with several hundred rows and columns. And under the hood, it just computes the inverse of the matrix A and keeps applying that inverse, modulo some number. So integer matrix library. It's a standalone C library. So if you ever find yourself needing this, it's available. All right, so all that was just meant to motivate why the inverse isn't a completely contrived thing that is often you'll see the presentation in a book or something, and basically they introduce something that seems like a massively harder way of doing something you already know how to do. But actually it's a really useful device that can solve many different problems far more efficiently than you would otherwise be able to do. Okay, so now what the heck is the inverse? So here's a definition. So we'll start with matrix A. Here A is a matrix. And here's my formal definition. So you'll want to be good at understanding what this means. And inverse of A, if it exists, and it need not exist, like the zero matrix doesn't have an inverse. If it exists, is a matrix B such that A times B is equal to B times A is equal to the identity matrix of the appropriate size. For this to even get going in the slightest bit, you need that the matrix A is square. So I'm only talking about a square matrix here. I won't talk about a non-square matrix will not have an inverse, so a square matrix. There is a notion of a left inverse and a right inverse, and then you can have one of those for non-square matrices, but we won't talk about that further. So there it is, that's the definition. But it's an important definition, and it can be surprisingly hard to work with. All it is, though, again, is just a matrix. The an inverse of a matrix is another matrix with the property that when you multiply the two together in either order, you get the identity. Or the identity is the diagonal matrix whose entries are all 1. It's called the identity because if you multiply it by anything else, you just get that something else back. All right, so then it's a definition, and the best way to understand a definition is to just kind of practice with the definition. So first I will write down a couple of matrices on the board. Tell me whether or not they have an inverse. So there's two ways to practice with the definition. One is you can make up little questions that involve the definition, and the other is that you can try to kind of prove things that involve the definition. Like with the transpose, we practiced with it by proving that A times B, the quantity transpose is B transpose times A transpose. Okay, does this 1-by-1 matrix with the entry 0 in it, does it have an inverse? Nope. Does this matrix 5 have an inverse? What is the inverse of the matrix 5? 1/5, that's right. So this matrix, I'll use the notation inverse like that. I mean the inverse of this matrix. So here we'll write B is A inverse. Okay, what about this matrix? 1, 2, 3, 4. Do you think it has an inverse? Seems possible? Not so clear. I mean, it doesn't look like the 0 matrix, so there's no obvious reason it wouldn't. Let's come back to that one. Let me make one where it's easier to see that it doesn't have an inverse. I gave that away. What about this 2-by-2 matrix? No inverse. Because look, there's a 0 there, so you're not going to be able to multiply. I mean, it's a little harder to see, but if you multiply this by some other matrix, say A, B, C, D, and you'll end up getting 5A, 5B, 0, 0. Doesn't matter what you put in for A, B, C, and D, there's no way in hell that you're going to get the identity matrix out here. Yes? The identity matrix is the diagonal matrix whose diagonal entries are all 1. and it's zeros everywhere else. So the question I'm asking now is if you take the matrix 1, 2, 3, 4, is there some other matrix whose entries are, say, maybe A, B, C, D, so that when you multiply it all out, you get the identity matrix. That's the 2 by 2 identity matrix. So what do you think? Could you even answer that question? Do you have any tools at your disposal to answer such a question? Probably is. And what do you think about that one right there?
Just
Alright.
likely.
This one's likelier?
No, just as likely.
Just as likely. Okay. So let's see how we can figure this out. First, this is actually just a system of linear equations, really. It says that so the coefficients are here. It's kind of like two systems of linear equations, really. Let me write down two things that look just like this ax equal to b thing, that if you solve them would give you this matrix. So you take 1, 2, 3, 4 times AC equals 1, 0. So remember how matrix multiplication works. Here, if you take this matrix and apply it to the first column, that gives you that first column. If you take this matrix and apply it to the second column, that gives you the second column. In other words, if you take this times that gives you that entry, and then this times that gives you that entry. And similarly, first row times the second column gives you that entry, and then the second row times the second column gives you that entry. So the question of whether or not there exist numbers A, B, C, and D that work in this equation is exactly the same as the problem of solving this these two equations. 1, 2, 3, 4 times AC equals 1, 0, and 1, 2, 3, 4 times BD equals 0, 1. Okay? And you know exactly how to solve that sort of thing. You could just compute the reduced row echelon form of the augmented matrix 1, 2, 3, 4, and then 1, 0, and the augmented matrix 1, 2, 3, 4, and then 0, 1. And in each case, you would be able to see whether or not there's a solution, and moreover, you'd be able to read off the solution if there is one, or all of them. Okay? Does that make sense? So let's just do it. So we'll make our little augmented matrix. 1, 0. And you know, as you go along and do this, we're gonna do row operations. I mean, we're not gonna go very far because it's just a 2 by 2 matrix, but we're gonna do row operations. We might as well just put this other column right here because it's not gonna make any difference. We're not doing anything. I mean, if we just throw another column in, what's gonna happen to that column? It's just, it doesn't matter. It's gonna be exactly the same as if we did it separately. Because all the action's going on here in the first two columns. So instead of doing it with just one column, I'm going to do both of them at once because I'm lazy and I don't want to have to separately do the entire row echelon procedure for each of the columns. Because at the end, this matrix is going to be exactly the same when I do it for this one or for that one. Okay? If I were to do them separately, I would end up applying exactly the same operations to this column and to this column. So let's just do it all at once. Okay, so what do you want to do? Well, take the first row, multiply by -3, and add it to the second row. That's what I'll do. So I'm clearing the first column. So I'll just leave the first one the same. And the second one I get 0, -2, -3, 1. Okay? I just took the -3 times the first column and added it to the second. And now I will rescale the second column so that the leading coefficient is 1. So I'll do that by multiplying through by -0.5. And I'll leave the first column the same, unchanged. 0, 1, 3 halves, -0.5. Okay, and now I'll add -2 times the second row to the first row. Have I messed up yet? Because I usually do whenever I compute an echelon form. Let me know when I do. So I'm going to take -2 times the second row and add it to the first row. And I get, so the second row is going to remain unchanged. So I'll just write it down. But the first row will change. So I'll get 1, 0. And then it gets a little hard, but I get -3, Okay, add that to 1, so I get minus 2. And then here, I get 1. You're right. So, right here you have, well, first, if you write down the corresponding systems of equations, do they have solutions? Can you read off the solutions? You sure can, because it's just x1 equal to minus 2, x2 equal to 3/2. That's one of the systems. And the other system is x1 equal to 1, and x2 equals minus 1/2. Okay? So now we've done this work. I probably made an arithmetic mistake along the way, but here's the cool thing. You can always just check at the end to see whether it works. I'll just let A, C be these two numbers, and B, D are those two numbers, and let's try and check to see if, in fact, this works. If it does, we'll have found the inverse of our matrix, and we'll also be confident in our arithmetic. If it doesn't, well, then we know there's an arithmetic mistake. So I'm just going to take the matrix 1, 2, 3, 4 and multiply it by A, B, C, D. Where A, B, C, it looks like it's exactly this matrix right here. It's kind of cool. Minus 2, 1, 3/2, minus 1/2. So it's a little tedious, but minus 2 plus 3, that's 1. Ooh, that's a good sign. And then 1 plus minus 1, which is 0. Oh, that's great. Now minus 6 plus 6, so that's 0. Cool. And now 3 minus 2 is 1 again. Whoa, so it worked. So amazingly, it seems that I didn't make any arithmetic mistakes. And in fact, we have found a matrix, A, B, C, D, that has the property that when you multiply it by 1, 2, 3, 4, you get the identity matrix. So you are right, that matrix is in fact invertible. Okay? Yes?
Is there a reason for doing brackets on rows and for like the matrix?
I like both brackets and parentheses, so I randomly use one or the other. But there's actually no reason at all. I can never make up my mind which one. It depends on my mood. So there's actually no reason at all. Okay, it looks like we're coming to a close. What I want you to do before next time, so tell me right at the beginning of class what happens next time. Does this one have an inverse? Exactly the same procedure will work to tell you either yes or no. What you do is you take this matrix and then put 1, 0, 0, 0. Basically just do the same thing but with an augmented matrix that looks like this. 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? And what you'll do is compute the reduced row echelon form and see whether you get a solution to each of the equations that come up. Okay? It's just exactly what I did, but for a 3 by 3 matrix. And at the beginning next time, I want you to be ready to tell me either yes or no. This has an inverse, and if so, what it is or not. Yes?
So would it not have an inverse if you don't get the identity matrix?
Yes,
on the
that's right. Yeah, so the question is, do you get the identity matrix here? And if you do, then that matrix over there is going to be the inverse, which is really nice.